Okay, so let's start. Sorry for the delay. Okay, today we are going to get into the algorithm for path computation. And as I anticipated, these algorithms are mathematical tools which usually relies on a representation of the network, which is called graph or digraph. This stays with for direct graph in case arcs of the graph have a specific direction. So the graph is defined by the set of the nodes, you can call it n, and the set of the arcs, where an arc is basically an ordered pair of nodes, and it corresponds to a connection on the physical layer. Here you see an example of a graph, and since we are talking about routing, we will focus on the detection on the graph of sequences of nodes from a source to a destination. Generally, a set of nodes from a certain node n1 and a final node nl is named itinerary, and is a subset of the node set, and it also since from one node to the next in the itinerary there is always an arc, it is also a subset of the set of the arcs. When the itinerary has no repeated nodes, it is called a path, and we are interested in paths. And a cycle is a path where this starting node is coincident with the last node, but we are not interested in cycles. Actually, we want to avoid cycles. A connected digraph is a graph where each pair of nodes has a path that is connecting the source of the destination. So for each pair of nodes, there is at least one path from node I to node J. Since we have to find the best route, not only a possible route, we need a metric, and on the graph, the fact of having a metric corresponds to an association of weights to each of the arcs. So each arc in the graph is a weighted arc, and weight Dij is the weight associated to arc Ij, which is a number, of course. Then the meaning of this number depends on the metric that you choose. And once you have defined weights, then we can also provide a length for an itinerary or a path, which is the sum of the weights of all the arcs that are crossed by that path. In general, it's also possible to associate weights to the nodes. In that case, the length of the itinerary will be the sum of the weights of the arcs plus the weights of the nodes that are crossed by the itinerary. Okay, this so far is very simple. So the problem of the shortest path is defined this way. Given a directed graph where n is the set of nodes and a is the set of arcs and g is the graph, and given two nodes I and j, we have to find the path of minimum length among all those that takes from I to j. And as we said, the problem has a polynomial complexity if you use the suitable algorithm to solve this problem. And there is also this property that we have to take into account. If a node k is spanned by the shortest path from I to j, so it's an intermediate node in the shortest path, then the subpaths from I to k and from k to j are also minimal, so they are shortest paths as well. And the set of shortest paths from all the nodes to a destination, in case of IP protocol, form a tree. So now we have an example. This is a graph where all the nodes corresponds to routers, and links corresponds to the point-to-point links or networks between the routers. and this is the set of routers and the set of links. This is the abstraction that we can use to find the shortest path, and for in the meaning where the nodes are routers and the links are connections between routers is useful at layer 3, but the same representation can also be used in other contexts. For example, if we are at the application layer, this may be also used to find connections in a peer-to-peer service. So given the cost of the links, the cost is always a number, as we said, but the meaning is different according to the metric. For example, it can be assigned by in a fixed form by the network administrator. In that case, the metric is called administrative cost, but it can also be, let's say, proportional to available bandwidth, inversely proportional to congestion, and so on and so forth. So since we have the links and we have the costs between the links, then the cost of the path is the sum of the costs of the links. And so the basic question is, what is the minimum cost path between the source and the destination? And in order to answer this question, we have to exploit a routing algorithm. So now we are going to look at the most important routing algorithm in our case, Bellman-Ford and Dijkstra. And first we define this algorithm using the graphs, and then we will see what is the implication when you have not a graph, an abstracted graph, but an IPNet. So let's start with the Bellman-Ford. The Bellman-Ford is able to find the shortest path in a polynomial time in each directed graph where you can have both positive or negative weights on the arcs. The only assumption is that there is no cycle of negative length. Otherwise, if you have a cycle of negative length, the shortest path between the source and destination, if they are on the cycle, would be to indefinitely circling the cycle or looping the cycle, because each time you make a loop, your cost decreases. So under these two broad conditions, we can always find a path, the shortest path with the Bellman-Ford algorithm between a source node and the destination. And actually, the algorithm can be used in two ways to find the path between a source node and all the other nodes, or to find the shortest path from all nodes to a destination node. Okay, they are exactly the same problem. It depends only on the application. So what is if you see a source node and you want the minimum shortest path tree getting to that source node, you will use this kind of application. If instead you want the minimum shortest path tree that is rooted at the source node, you will apply it in this other way. So let's look at the formal definition of this algorithm. In order to run it, we need a set of variables, and these variables are named in this way, capital D sub I, and this is say exponent is H, small h, and the definition of this symbol is the length of the shortest path between a given node I and the source node. Here we imagine that we apply it source-wise, so from the source node to all the other nodes. This shortest path consisting of a number of arcs which is less or equal to h. Okay, so we will see immediately that basically this h is like horizon boundary that limits the topology that has been discovered by the source node. So this is each node in the network will have its variable, which is this one, and we have an initialization step that consists in setting this variable equal to 0 in the case of the source node, and it will remain always 0 throughout the whole algorithm. Then we can initially set all the variables of all the other nodes to infinite. Okay, and H not only has the meaning of the boundary of the topology discovery horizon, but it also numbers the the iterations of this algorithm. This is an iterative algorithm. So H is also the index of the iteration. So in the first iteration, H is equal to 0. So this is the initialization of all the D variables of the nodes which are not the source node. The core of each iteration is this expression here. This is the expression that tells you how to update in iteration h plus 1 the D variable of a generic node I, starting from the values of the D variables in the previous step, in the previous iteration. So this is the expression, the updated value of the I would be the result of the minimum between what was the value of the I in the previous step and this expression here. Okay? This expression is the minimum, let's say, taking all the other nodes as pivot between the distance that is evaluated by summing the distance at the previous step of each other node plus the value, the cost of the link that is connecting this variable node with node I, which is the node we are identifying. Now, this is very difficult to explain in words, and so we have to look at an example to understand it better. So the algorithm terminates in h steps, and this h is the maximum value that the variable small h will get into the algorithm. What is h? It is equal to the network diameter, so the maximum between the distances measured in hops, so in number of links crossed, between all the pair of nodes in the network. Okay, so you have to take all the pair of nodes, I and j, assuming that you know what is the minimum distance in terms of number of links crossed. You take the maximum of these values, and this would be the network diameter. And this network diameter is will be the maximum value reached by h when you are repeating the steps of this algorithm. And this network diameter can be proved to be always less or equal to n minus 1, where n is the number of nodes in the network. Why this expression is useful? Because this will give us an indication of the complexity of the algorithm. So in the worst case, h would be equal to n minus 1. So let's explain better what is this updating step in each iteration. So let's assume that we are considering this network. This is the source node for which we want to calculate the tree of shortest paths from this node to each other node in the network. Then in this specific iteration, we want to focus what happens when this index I is corresponds to this node D. Okay, so we are assuming that we are updating di sub I at the next step, h plus 1, of this specific node D. Then we will have to repeat this updating operation for all the other nodes different from S. Okay, so now we are just focusing as an example on node D. We can assume that the distance at the previous step of node D, so D sub I, where I is equal to D, was equal to 20. So this value here that goes into this minimum was 20, okay? Is 20 actually. Now we have to compute the other values. So we have to take D as the pivot, let's say, and then walk on the network and consider each other nodes, and then calculate this value here, which is the distance of the other node plus the link that is connecting node J, which is the current the running variable, to node I. Okay, so this is a table. You can see here J, which will take all the values that corresponds to S, A, E, B, and so on and so forth, except D. And then this is the distance that node J had at the previous iteration, which compares here. And this is the value of the link that is connecting node J to node I. Okay, and this is the calculation of the final element that we have to compare in this argument here. So let's start. Of course, numbers are arbitrary, okay, in this example. So this is the first node S. So the distance by definition is always 0 at all the steps. And the S and D are connected by this direct link, which is 11 and as a cost. So the final element here would be 11. Okay. Then we can take another node, for example, A. As you can see, A and D are not connected by any direct link. Okay, so here you have a value of the distance of A at the previous step, but when there is no physical connection, so there is no physical link in this topology, then we can assume that the cost associated to the arc ij is infinite, okay, because there is no actual arc. That is the same saying that the arc is infinite. So in this case, obviously the final result would be infinite. The same for B. Instead, C is directly connected to D. C had in the previous step a distance of 4. Dij, that is this link CD, has a weight of 3, so the final result is 7. Okay. And so on. You have to iterate on for all the values of possible values of J different from I. Okay. Of course, it doesn't make sense to see what is the distance of D from itself. So this is what you have to consider each time you need to update a weight of a given node. In this case it was D. Then you have to do the same for A, for B, for C, and so on, each time with this table. And in order to take the final decision, you have to take the minimum between all these values. In this case, the minimum is 6 because DIH was 20, so much larger, and the minimum of all these elements is 6. Okay? So finally, this DIH plus 1 will be equal to 6 in case I equal to D. Okay? We can notice a particular feature of this updating process, that all the nodes that are not connected directly with node I, which we are taking into consideration, they will have Dij by definition equal to infinite. So they will never have an impact on the final decision because, of course, infinite is larger than all the numbers. So basically, we can neglect these nodes A, B, F, and G when we are considering node D, because node D is not directly connected. Or said in in other words, when you are making this update and you are taking a certain node, in this case is D, you have only to consider the neighbors of this node. Okay, just the neighbors of this node will have an impact on the updating process. So we can constrain the set of nodes that we have to inspect just only to the neighbors of node I. So this is the final, the global definition in terms of pseudocode of this algorithm of Bellman-Ford. And basically you can see that always this comparison is at the core of the node. There is an error here. This is no, actually there should be another minimum, and then this minimum should go inside on the inside of the outer parentheses. I have to correct this expression. However, also if you write it in this way, it's not entirely wrong. The only thing is that you have always to compare this J with the I. The closing condition for the algorithm is that the updated value of the distance from the source does not change in one step compared to the previous step. Okay, so when this is realized for all the values of I, so for all the nodes, then you can stop the algorithm. And it can be proved that this happens when h has reached the value of the network diameter, as we have already mentioned before. So let's take another example. This is a very simple network. We take this node as a source. We want to calculate the shortest path from this node to all the two other nodes, basically. So initially we have these conditions. The 1 is set to infinite and the 2 as well. Then we have the first iteration. So if you take, for example, 1, which is this node, you have to compare the previous value of the cost, that in this case is infinite, with just two other values, which is the distance of S at the previous step, plus the link, which is 1, and the distance of 2, node number 2, plus the link, which is 1. But node number 2 in the previous step was at an infinite distance. Okay. So the result here is 1. And the same for D2. You have to compare the distance of the previous in the previous step, which was infinite, distance of the source plus 3, which is this link, and the distance of the other node at the previous step, which was infinite, plus 1. So the result is 3. Second iteration. Now we have the minimum for D1, for node 1, we have the minimum between the previous distance, that was 1, then distance at the previous step of 2, which was 3, plus 1, 4, and distance of the source plus 1, which is again 1. So the final result is 1. Case of node 2, previous distance was 3. Then we have the distance of node 1 at the previous step, which was 1, plus 1 is 2. And then we have the distance of node the source node plus 3. Okay? The minimum is 2. And now we know that the algorithm can stop because in this network the diameter is 2, because the maximum distance between the nodes is 2 steps, 2 hops. Okay? But you can also check that this closing condition is met. You can try a third iteration and you will verify that the distances of 1 and 2 do not update. So the algorithm is over. Yes. I know, okay. This is basically the Bellman-Ford. Another example, this is a little more complex network. And now we start again. We want to find the shortest path tree that is rooted at A. So we consider this table. We have this. There is the list of the nodes. This is the first step. It's already the first step actually. So in step with h equal to 0 would be that node A has distance set to 0 and all the other nodes has a distance set have distances set to infinite. In the first step we have finite distance for node B and node F. You can notice that they are the two nodes which are directly connected with A. So basically they are one step, one hop away from A. Then if you go on with the other iterations, the second iteration, this is the state and this is the corresponding table. Okay. Actually, when you want to build the shortest path tree, not only you have to consider the distances of the nodes, but also what is the node which is connected, the previous node the closest to the source, which is connected to a given node, no? Because basically we are defining a tree topology. So this is what happens at step 2, then this is step 3, and this is step 4. I don't go into the details of the calculations, but if you want you can test it and you will see that these are results, hopefully. What is quite clear in this example is what I said at the beginning, that this index h is also the boundary of the topology discovery horizon from the source. In fact, you can see that initially the source only sees the first two links, so here the horizon is one hop. Then in this case you will find only paths which are maximum 2 hop away from the source. Okay. So for example here this is 2 hop away from the source. And then in this case you may have paths that are 3 hops away from the source. Here you have also another column with this indication of the next hop. And for example, if we take node F, node D. Okay, in step 2, node D is at a distance 9 and is connected to F, so it's reachable through F. So the path from A to D is this one. Okay, it's a 2 hop path. But if you go in step 3, now the distance of D has reduced to 6, and the previous node connecting D is E. So basically the path from A to D is A, F, E, D. It's a 3 hop path. Okay, 3 hop path. And then if you look at the step 4, now the path connecting D to A is A, B, F, ED. It's a for-hop path, okay? Because each time you add another step, the horizon of the topology that has been discovered increases by one hop. And then when you have reached this step h equal to 4, you can test that if you go further and you repeat other iterations, the situation will not change. So all the nodes will remain at the same distance and also with the same path. Okay. So this is basically the implementation of the Bellman-Ford algorithm in a centralized way, because here you can see that there is a table where you are noting iteration by iteration the state of all the nodes, and we are acting in this case as a supervisor which is able to know the situation of the network in a complete way. But we can also implement the Bellman algorithm in a distributed form, and it can be shown that the distributed form will converge in a finite number of steps to the solution found in the centralized case. How does it work? The distributed form exploits the fact that updates are only influenced by the neighbors of a single node. Okay? So based on this fact, the distributed form of this algorithm requires that each node periodically sends updates to only its neighbors. Okay, so a node will receive updates from all its neighbors periodically, and thanks to the updates received by the neighbors, the node is able to update its own distance from the source, okay, in each step of the algorithm. The order in which these updates arrive to this node, so if it is first sent by a first node or a second node, or if the updates arrive together, or if they arrive in different steps, this order is completely irrelevant, because all the updates contains information at the previous step. Okay, so information that is already consolidated, and therefore then this node is always able, regardless of the order of these messages, to update its own distance from the source. So actually, since we want to be effective, when the Bellman-Ford algorithm is performed in a distributed form, we don't consider a single node as a source, but we consider all possible nodes. And of course, speaking about sources or speaking about destinations is the same. So each node basically gets updates from all its neighbors about the distances from of these neighbors from all the other potential destinations, all the other nodes which are potential destination of traffic. So in order to if we want to show the algorithm, the Bellman-Ford algorithm, using basically piece of paper and a pen, what we can do to practically solve this algorithm in a reasonable time is the following. So we can label all the nodes with two labels, two digits. Variable n is the next node on the shortest path, and variable L is the length of the shortest path. In this case, we refer to a specific source of the for all the nodes, so a single source. Then we update the labels by looking at the labels of the neighbors and doing updates according only to the labels of the neighbors. Again, the order does not matter because of the property of the distributed algorithm. When labels don't change anymore, we can build a tree of the shortest paths by tracing labels back. So the shortest path from a source to each other node will be given by the sequence of labels that you find along the path. Let's take an example. So in this case, we are always referring to a single source. Okay, so this is not exactly the distributed form that is implemented by the distributed protocol that we will see later on, but it's again a form to solve to quickly solve the Bellman-Ford algorithm in a let's say centralized way, considering a single source, not all the possible sources, and taking always into account the full topology. So we first label all the nodes. This is the source node, so it will be so the previous node will be always itself, and the distance from itself is 0. In all the other nodes, we leave unspecified at the moment the previous node, and we set the distance to infinite. Now we start the first iteration. And in this case, the only node with the final distance is node 1, which is also the source, and it has only 2 neighbors. So this node here will have this node 1 as a neighbor. In this case, arcs are also directed. This may be not the general case, but with directed arcs, you simplify a little bit because you have less neighbors. So now node 2 have a single neighbor, which is 1. Node 4 has two neighbors, 1 and 2, but 2 has an infinite distance, while 1 is the only one with a finite distance. So when we update the labels of all the nodes, we just have to update the labels. We actually have to update the labels of node 2 and node 4. Labels of node 1 never updates because it is the source. Sorry, I made a mistake. There is also node 3, which has a neighbor with a finite distance, which is this one in the previous step. Okay? So we have also to update the label of node 3. Label of node 2, we take the label of its neighbor, which is 1. The distance is 0. Okay? We have to sum the link between 1 and 2. There is a direct link with distance with a weight 2, so the distance will be 2. Okay. Node number 4, there is a direct link with node 1. The weight is 1, so the new distance will be 1. Node number 5, again, there is a direct link with 1. The cost is 5, so new distance is 5. And since we updated these all these 3 distances of the nodes, considering the distance of node 1, then node 1 is always in all the 3 cases is the previous node. Okay, so we write 1 here in the first position. Then next iteration, label of node 1 doesn't change. We have to update the label of node 2, but the label of node 2 doesn't change because the only neighbor is 1, which has the same label as before. Now, label of node 3. Okay. Now we have actually 2 nodes which are neighbors and have and had finite distance in the previous step. Node number 2 and node number 1. Okay. The distance of node number 2 was 2 plus 3, which is the direct link, is equal to 5. the instance of node number 1 was 0 plus 5 equal to 5. Here we have an equal condition, so we can choose either to leave the original entry that we had in the previous step, or to update it, but it will have the same value of distance as before, as in the other case. So we decide to leave the same status as the previous step. So it is 1 as a previous node and 5 as distance. Node number 4, here we have two node neighbors, node 1 and node 2. And node 1 has a distance 0 plus 1 is 1. Node 2 has a distance 2 plus 2 is 4. 1 is less than 2, than 4, so we leave the same label as before. Node 5, we have to update it. The only neighbor is node 4. Node 4 had the distance in the previous in the previous step equal to 1 plus 1 is 2. Okay, so this is the new label. Node 6 had has two neighbors, but one in the previous step had distance infinite, so it doesn't count. The second one is node 3. The distance of node 3 was 5 plus 4 is equal to 9. Next and the last step, so node 1 doesn't change, node 4 doesn't change, node 2 doesn't change. Node 3, now we have also a new neighbor which had a finite distance, which is node 5, and the distance was 4 plus 1 is equal to, was 2 plus 1 is equal to 3. 3 is less than 5, so we update it. The next, the previous node is now 5. And in case of node 6, we had previously the distance of 9, but now considering node 5 as a neighbor, which had a distance of 2, plus 2 is 4, is less, so we update. Okay, so this is the final condition. You can check that if we go on to do other iterations, we will always obtain the same labels. So the algorithm is over. Okay, and this is what we obtain as the tree of shortest paths from this node to all the other nodes of the network. Okay. Questions? So let's look at the other algorithm, which is Dijkstra. And here we have a similar set of variables that we need, but managed in a different ways. So again, we have arcs with weights, and the Dijkstra algorithm has a narrower application field compared to the Bellman-Ford. It works only when arcs are all positive. So if you have negative arcs, you cannot apply the Dijkstra algorithm. You have to apply the Bellman-Ford. But we will see that Dijkstra is less complicated than Bellman-Ford, of course. So the aim is to find the path, the shortest path from a certain node that we can choose as a source to all the other nodes in the network. And here we have to define again a set of variables which are the distances of the distance of all the nodes to the source, and these variables are updated each time we do an iteration. But then we have also to set another variable which is actually a set, is a subset of nodes, and is the subset of nodes that corresponds to the already calculated shortest path tree. Okay, so the tree of all the shortest paths starting from a given source and going to the other nodes is a set, and this set is updated during the execution of the algorithm. At the end, this set will be equal to the will contain all the nodes of the network. When this set contains all the nodes of the network, it means that we have calculated the shortest path from the source to each other node. And so the condition of termination of this algorithm is when P contains all the nodes of the network. So it's coincident with N. Initialization is similar to what we have seen before. We can set the initial value of the distance of the source to 0, and this will remain the same. And then we can set the distance to all the nodes from the source equal to the direct link between the source and the node. And in case this direct link does not exist, is not a physical link, then we can assume the distance equal to infinite. Okay. In case we have nodes that are directly connected to the source, in the initial step we already upload the cost equivalent equal to the direct link into this running variable, which is the distance. And this is the pseudocode. So initially we have to take all the nodes that are not included in P, so that they are not already in the tree of the shortest path tree, the shortest paths. And we have to select the node which have the minimum distance to the source in this set, which is the set of all the nodes minus the set of the nodes that are already included in P. So once we have identified this node will enter into P. So we will have to connect this node into the set P. Of course, connecting the node, considering what is the previous node on the shortest path that is going to the node that has been identified. Okay. Then we check the set P. If it contains all the nodes of the network, we can stop the iterations. Otherwise, we have to go to the second step. And now we have to take all the nodes that are not in P, but they are neighbor to P. Being neighbor to the set of P means that this node J that we are identifying has at least one direct connection, so one direct link with one of the nodes in P. Okay, so it's connected with at least one of the nodes in P by a direct link. So for all these nodes which are not in P but are neighbors of P, we have to do this update of the distance. So the new value of the distance will be the minimum between the old value of the distance and the minimum that is calculated similarly to the Bellman-Ford algorithm, but considering only nodes that are inside P. Okay? So you have to consider all the nodes that are in P, so this key belongs to P, and consider their distance that they had, the current distance that they have from the source, sum to this value the distance, the cost of the link between key and J, and then take the minimum of all these values. Okay. Since we are doing this first step, it means that at each node we are adding another node to P. Okay. So in all the possible cases, you're always adding a new node into the set of the minimum path trees, in the minimum path tree. Since the condition of termination is that P contains all the nodes of the network, then immediately this tells you that this algorithm will take always exactly n steps, okay, where n is the number of nodes in the network. So the number of iterations in this case is not related to the diameter of the network, but simply to the number of nodes in the network. So if we want to again solve this algorithm with a piece of paper and a pen, we can adopt the same procedure as in the Bellman-Ford, with the only difference that in this case we will have permanent labels and temporary labels. So in each iteration we will only update the temporary labels, and in each iteration there will be one more label that becomes permanent, okay, until you don't have labels anymore to update. So at the beginning you have only one permanent label, that is the source label, and then at each iteration the temporary label with the shortest length becomes permanent. And this is because the node which is shorter to the source and is not already in the set P will become part of the set P. So let's take the same example. Okay, here you have initially the source node, which is distance 0, and in the first iteration we already set a distance. We already set all the distances of the nodes that are directly connected to the source to a finite value. So we will have here this node, which is a distance 2, this is a distance 5, this is distance 1, because we have these three links which are direct with the source. And then the other nodes remains with infinite distance, because they are not directly connected to the source. Now we have P, which contains only one, which is the source. We have to identify in all the other nodes, between all the other nodes of the network, which are not in P, what is the shortest, the one with the minimum distance. And in this case, the one with the minimum distance is node number 4. Okay. So now node number 4 becomes part of the set P, and its label becomes permanent. So it will not be updated anymore. And so it becomes red. Okay. Now we have the updating phase. We have to take all the nodes which are not in P but are neighbor to P and update their distance. And now P contains 1 and 4. So the neighbors of P are node 5, node 3, and node 2. Okay, they are all neighbors of P because they are connected to at least one node which is in P. So we have to update their cost considering the nodes which they are connected to, and looking if the sum of the previous cost of that node plus the direct link is less or equal to the cost in the previous step. Okay? So we do this with node 2, node 3, and node 5. In case of node 2, previously we had distance 2, now we have again distance 2, is 0 plus 2. Node 5 is connected to node 4. So previously we had this infinite distance. Now the new distance will be 1 plus the distance of 4, which is 2. And node 5 is only connected to node 1, so it doesn't change compared to the previous step. Now we have again to identify between all the nodes that are not in P, what is the one with the shortest distance. And here we have we have an equal situation. Node 2 and node 5 both have a distance equal to 2. Okay, so we can choose one of the two. For example, we choose node 2, which becomes part of P, and its label becomes permanent. So now we have the set of nodes which are not in P. We have to consider the neighbors of the nodes in P, and the neighbors are again node 3 and node 5. Node 6 doesn't have any direct connection with the nodes in P. So we update node 6 and node, no, actually we should update only node 3 and node 5. Node 6 is still without any connection. So here we should wait to write this, but it doesn't change anything. Now the new labels are, in case of node 3, we have now the connection with node 2. Plus node 2 has a weight 2, distance 2 plus 3, it becomes 5. Node 2 has a distance distance 2 plus 3 becomes 5. Actually, we should wait also for this update. So these two updates of node 3 and node 6 should come in the next step. Now we have node 5, which is still the same at the same distance, because we have 1 plus 1, which is 2, and node 3 should be at distance 1, and distance 5, and node 6 should be a distance infinite. But when we are searching for the new node that has to be included in P, then we will have to include node 5. Now at this point, node 3 and node 6 becomes neighbor of the set P. 6 becomes neighbor of the set P, and node 3 can be updated considering the distance of node 5. The distance of node 5 is now 2 plus 1 is equal to 3, which is less than 5. So we can update the distance of node 3. And also in node 6, now we have a direct connection with node 5. And so the distance is 2 plus 2 equal to 4. So now we have these two nodes, 3 and 6, which are the last one that are out of P. We take the shortest one, which is node 3. It becomes permanent. And then we will have only node 6. We have to update node 6. In this case, the distance of node 3 is 3 plus 4, 7. Which is more than 4, which is the previous distance. So we keep the same label as in the previous iteration. And now we have also node 6. So now all the nodes are in the shortest path set. And the final solution of the shortest path 3 is the same as in the previous case. So the Dijkstra algorithm and the Bellman-Ford algorithm are converging to the same solution when we are performing them. This is another example with the same network as the previous one, and I don't go into the details. This is the sequence of the P that you obtain with the neighbors of P. So P is initially A, then it contains A and B, and the neighbors are these three. Then it contains A, B, and F, then A, B, and F, and E, and then A, B, F, E, and C, and then all the network nodes. Okay? And the final result is again the same as the Bellman-Ford. Now you can then do the algorithm in details as an exercise. So the complexity of these two algorithms is polynomial, and in fact, if we calculate the complexity of Bellman-Ford, in the worst case, we see that we need n-1 iterations, because in the worst case, this is a diameter of a network with n nodes. Okay? And when we perform each iteration, we have to consider n-1 nodes, which are all the nodes except the source. And for each of these n-1 nodes, what was given by the index I when we wrote the algorithm. For each of these n-1 nodes, we had to consider n-1 comparisons, because for each I, j was the running variable that spanned all the nodes except the node that is was equal to I. Okay, so if you put these together, it makes the complexity big O of n to power 3. Big O means that when n tends to become large, so tends to infinite, the real complexity that we actually don't know exactly, which is a function of n, will never be less than this function that we know, of course. In case of Dijkstra, we have always n-1 iterations, and then on average, we have n operations per iteration. So the complexity is less than the Bellman-Ford, is only n squared. So the Dijkstra is generally more convenient. Okay. So far we have seen the implementation of Bellman-Ford and Dijkstra in a centralized way, and we also, let's say, already anticipated some features of their distributed implementation. But when we want to use this algorithm for routing protocols in IP, we need the distributed form of both the algorithms. So now we are looking at the distributed form of Bellman-Ford and Dijkstra, and these two forms take the name of distance vector routing in case of Bellman-Ford and link state routing in case of Dijkstra. They are just a distributed implementation of the Bellman-Ford and Dijkstra. So when we are considering routing algorithms that have been actually applied to internet, the distance vector was the first one, and it was used in ARPANET, the origin of internet, until the beginning, and it was based on a metric which measured the length of the queues on all the routers in the network. That is more or less equivalent to the delay met by the packets, and so it was not related to the speed of the links. Then other metrics were also proposed, but in all the cases, distance vector is characterized by its slowness to converge in dynamic situations. So this is why it was abandoned at a certain point for a new algorithm, that is the implementation of the Dijkstra algorithm in a distributed way, which is based on a link state. I think the year here should be changed because it's the same as before, but it's a later time. So in case of the link state, the principle is that each node measure the distance to all its neighbors using, for example, a metric based on the delay, sending messages to all its neighbors and waiting for the replies. And then once the node has collected all the distance values, it will communicate all the set of distance values from all its neighbors to all the other nodes in the network. Okay? So in this case, in the distance vector case, the exchange of messages between routers is limited to the neighborhood. In case of link state, each node, so each router will have to send updates to all the other routers using the flooding technique. So it means each message is replicated for all the other routers. And then each node is able to take all these indications of link state and build and then construct the minimum distance paths. And also the updating period was shorter with the new algorithm. We have another type of algorithm which is used in the internet routing, which is a path vector. And it's like an hybrid between distance vector and link state. In this case, the routers exchange information with the neighbors, like in the distance vector case, but this information contains not just indications of distances, but they contain sequences of nodes. Okay, so this information contains paths, and this algorithm here, the path vector, is not used inside the autonomous system. If you remember, we mentioned at the beginning that we have autonomous systems. Inside the autonomous systems, you have a routing system which is run with certain routing protocols, and then you have the routing between autonomous systems, which is managed by another type of routing protocol. Okay? So path vector is used for the inter-autonomous system routing, so routing between autonomous systems. And there is another protocol which is different from the one that is based on distance vector, and also from the one that is based on link state, which use this path vector algorithm. And so, since it is used between autonomous systems, the paths are not sequences of routers, but are sequences of autonomous systems. Okay? So each node of this path is an autonomous system. We will mention the protocols, but only briefly because we don't have time to go into the details. Now let's focus on the algorithm, and we consider only distance vector and link state. The type of information that is used in these routing protocols can be also classified according to this other criterion, if it is a global information or a decentralized information. When the information that is available to a router in order to calculate the shortest paths is global, it means that the router has the visibility on the complete topology of the network and have cost and has information about the cost of each link. And this is typical of the link state protocols. Okay? So in case of link state protocol, each router can reproduce the complete topology of the network. Instead, in the case of distance vector protocols, the routers does not need to reconstruct the full topology of the network. They just need to receive values of distances. So they just need the list of the distances between themselves and all the other destinations in the network. And they compute and update this list according to the messages that are received from the neighbors. Okay. So each node has its own list. Each node will communicate its own list to its neighbors, and then each neighbor will take all the lists from that have been gotten from all its own neighbors, combine them so to update its own list of destinations and distances towards destinations. Okay, so there are different type of information. So let's start with distance vector. In case of distance vector, the output of the distance vector is finally a routing table that specify what is the minimum distance between one node and each other nodes, but also which is the node to use as next stop. And so it comes from the Bellman-Ford, which can be implemented in a distributed or centralized way. In case of a distributed implementation, we are talking about the distance vector protocol. So algorithm. So in the case of the distance vector algorithm, each node receives the estimation of distance from its neighbors and computes its own list of distances. In order to do this, however, the node must be also aware of the weights, the cost of the links that connects itself to its neighbors, because each time the node receives an information of distance from a given neighbor, it has always to add to these distances the cost of the link between the two nodes. The algorithm is called the distance vector because it's based on an exchange of messages, and these messages contains a vector, a list of entries, and each entry contains the address of a destination node, let's say a destination address, plus a value of distance. Okay, so when a node sends a message to another node, that is its neighbor, this message contains an array of entries, and each entry contains an indication of a destination address plus a distance value. The distance vectors are only sent to the adjacent nodes, so the neighbors, and they are sent periodically or as a result of a change of network topology. So when a node decided to change its estimation of distances towards the destinations, this node will send an update to all its neighbors. So the node sends a distance vector periodically or as a result of recalculation. We have already said that. And this is the recomputation of the distances. So when the node receives a distance vector that is different from what has been previously stored, then it has to recompute the distances, or also in the case when this node acquires a new neighbor because a new link from the node to some other node is activated, or when one of the links connecting the node to its neighbors goes down or goes out of service, because in this case the neighbor becomes unreachable. So all the distances have to be recomputed. The recomputation is again similar to what we have seen in case of the Bellman-Ford algorithm, but you have to consider that here we only consider the neighbors, so all the nodes that have infinite distance with this node here doesn't have an impact. And also we are considering a specific node. So this is basically the node that corresponds in the original Bellman-Ford formulation to node I, and these nodes here are all the other nodes which have a direct connection. So what happens when a node receives a distance vector from a neighbor? First of all, the node has to increment the distances specified in the vector by the cost of the ingress link. So this vector travels a link, which is because it is originated by a neighbor. So let's say that this neighbor sends a distance vector to this node. The node will cross this link, will enter the node by this interface. So the node has to increment the costs that are listed in this vector by the cost of this link. Okay. Then, once a node collects a distance vector and increments all the distances, it starts inspecting the content of the distance vector. Okay. So if in the distance vector the node finds a destination which is not already in the routing table, then a new entry in the routing table will be added with the destination distance value, okay? Mentioning as a next stop the node that sent this distance vector. Then, if the destination is already in the routing table, the node has to compare the updated value of distance received in the distance vector the node has first to check if the originator of the distance vector is the node that is mentioned in the routing table as next stop. Okay? So if the node that sent the distance vector for that specific destination is the next stop that is already in the table for that destination, then the node who received the distance vector will replace the information in the routing table with the new information, regardless of the values of the distance. Last case, the destination is already in the routing table. The node who originated the distance vector is not mentioned as a next stop in the routing table. In that case, the node who received the distance vector must check the value of the distance. If this value is less than what is reported already written in the routing table, then the node has to update the routing table. Otherwise, if it is more, the routing table is not updated. Okay, this is the process that is generated when a distance vector arrives to a node. As usual, an example is always more clear than an explanation in words. So let's take, for example, a node which has this old routing table. Here you can see here a set of destinations, a set of distance values, and next stops for each destination. Okay. So this node will receive a distance vector from node C. This is the distance vector from node C. It contains a list of destinations and a list of distances. Okay. Notice that in the distance vector you don't put also the next stop information, because it doesn't make sense, because you are sending to another node. You just copy the first two columns of the routing table. So node C, when node C sent this distance vector to our node C had copied the first two columns of its own routing table into the distance vector. Then, when this distance vector arrives to our node, first of all, this node have to increment all the values of distances by the cost of the link. So here, node C is connected to our node. We don't know the name, but it's a certain node. It's connected by a link which clearly has a cost 1. Okay. So all the distances reported here are updated. So 4 becomes 5, 8 becomes 9, 4 becomes 5 again, and so on and so forth. Yes.
They're updated. How? Why do we increase them by 1?
Because the node that is receiving this distance vector have has two informations. First, the input port of the distance vector, so it knows the link where the distance vector is coming from. Second, it knows also the cost of this link. Okay.
For the link between himself
And
the
C.
link and C.
And C.
But if the distance is q, why are we incrementing only one?
No, here the link is no.
I didn't understand. Because I see that the distance from the link that we are considering in C is q, but we're incrementing.
No, because what is written here not necessarily is equal to the distance of between C and the node that we are considering, because it can be an old value. Okay.
Okay.
The distance is something that may change.
Okay, so the real distance between the node we're considering as C is 1.
Is 1.
Okay.
The real distance is 1, and this is an old value that estimated the distance to be 2. So once the message has been received and it has been incremented, then we have to look at all the entries of the distance vector and check what to do entry by entry. So for example, in the case of network 1, that was originally with the distance 7, here the resulting distance will be no, there is no network 1 in the distance vector. Okay, so network 1 is not reported, and therefore the table remains the same. Okay, it doesn't change because we don't have news regarding destination net 1. Destination net 2, original distance here was 2. Next node was C. Now, actually, what I said before is not completely correct. So you cannot know, looking at this table, what is the distance of C between the node that is receiving distance vector. Okay, the distance of C is something that is configured. The cost of the link is something that is configured externally. Here the indication net 2 and C means that not C but the destination, which is named net 2, is at a distance 2 if C is used as next hop. Okay. So now we have to apply the second case, because the distance vector was received by C, which is mentioned here as next hop. So in this case, you have always to update, regardless if the new value is less or more than the previous one. And in fact, in this case, the distance of net 2 is 5. But since this indication comes from C, which is the next hop, the result is that the cost is updated. Okay, so net 2 becomes at cost 5. Then we have net 6. Net 6 was at cost 8. Now it's so in all the last three cases, 6, 8, and 9, this distance vector arrives from a node which is not mentioned as a next hop. So we have to do the comparisons. So in case of net 6, we had 8, and now with the distance vector, with summing the link, we have 5, indication of 5. So we have to update, because this means that net 6 is reachable with the shortest distance. Okay. So the update is net 6, 5, and then we have to replace the original next hop with C, because this indication came from C. Okay. So this entry was in the distance vector that was sent from C. So it means that net 6 will be reachable at a distance 5 if we go through C. Okay. In case of net 8 and net 9, in case of net 8, we have the same value, so we can decide what to do. Here we decided to maintain the same information as before. In case of net 9, the value that was received from 6 is 6, from C is 6, which is larger, so we don't update. Okay? And finally, we have net 3, which was not present in the routing table, so the node will add another entry in the routing table, taking information that was got from C. And this entry will be 9 and C. Okay, this is basically what happens when you have an incoming distance vector. Unfortunately, now it's quite late. This example is a bit long, so we will consider it next week. So next week I will try to close as quick as possible this part on the routing algorithm. Say something about protocols, but a very short indication, and then we will do probably exercise on routing, and let's say exercise on routing. Okay, this will be next Tuesday. Okay, thanks.